Welcome to this course in quantum mechanics. In this introductory lecture, we'll look at quantum states and the Copenhagen and the probabilistic interpretation of quantum mechanics. Let's start things out by looking at some classical mechanics. Here I have a coordinate system with a circle centered at the origin. I add a bunch of equally spaced holes to the circle, in this example 12. Then I have a ball represented by the blue dot, which can be positioned in one of these M holes. The position of the ball will be denoted by theta, and in a general setting where I have M holes, theta can take the value 0, 2 pi over m, 2 times 2 pi over m, all the way up to m minus 1 times 2 pi over m. In the example, m is 12, so theta can take the value 0, pi over 6, pi over 3, pi over 2, and so on. So let's move on to the wonderful but weird world of quantum mechanics, where we will begin by talking about quantum states. The blue ball in the classical mechanics example will now be replaced by an electron. We'll begin by assuming that space is discrete, so that the electron can only be found at one of m positions, just like in the classical system, and space is one-dimensional. Then, by letting m go to infinity, we'll see what the model will look like when space is continuous. And it's a fairly simple matter to increase the dimensionality of space from 1 to 3. To simplify notation, let's start with only two holes. We have a hole to the right represented by the angle 0 and a hole to the left represented by the angle pi. In the classical system, we talked about the position of the ball. In the quantum system, we'll instead talk about the state of the system. And the state of the system will be represented using this notation. This is part of the direct notation on which we will have a lot more to say later on. For this toy model of space, there are two states that are called pure states. Those are 0, represented by the right-hand hole, and pi, represented by the left-hand hole. So far, there is really no big difference between classical mechanics and quantum mechanics. The big difference is the following postulate of quantum mechanics. Any linear combination of the pure states is a possible state of this quantum system. That means that we can write theta as a linear combination of 0 and pi. We use the coefficient phi 0 times 0 plus phi pi times pi. Here phi 0 and phi pi are arbitrary complex numbers, with the exception that both cannot be 0. So the set of possible states of this quantum system is really the span of the two pure states 0 and pi. Again, this is something we'll have a lot more to say about later, but the consequence will be that the set of possible states will be a complex vector space with a dimension equal to the number of pure states. We're going to call such a state a mixed state, and as a simple example, we can consider a state where both phi's are equal to 1, so theta equal to 0 plus pi. The big question is then, what do we mean by a particle being in such a mixed state? Well, I think it's fair to say that nobody can actually answer that question. Some prefer to think of a mixed state like this as the electron not being in any of the holes. Others like to think of such a state as the electron being in both holes at the same time. Fortunately, though, there is a probabilistic interpretation of mixed states. And this interpretation goes as follows. There are equipments which can actually measure the position of the electron. And if we try to measure the position of the electron when it is in this mixed state, we will find that there is a 50-50 chance of finding the electron in the left hole and in the right hole. Let's say that we find the electron in the left hole. You may think that the electron was then in the left hole right before we made the measurement. However, this is not the view held by most of the physicists today. So instead, let's talk about the Copenhagen interpretation. According to this interpretation, again accepted by most physicists, it's the act of measurement that forces the electron to select one of the pure states when we make a measurement. The actual hole where we will find the electron when we make a measurement is selected completely randomly. That is, if the electron is in this mixed state, there is absolutely no way of predicting where we will find it when we look for it. It is kind of a spooky interpretation because it means that if we're not looking, then the electron is not in any of the holes, or if you like, in both of the holes at the same time. It's only when we decide to look that the electron is forced to commit to one of the holes. Of course, Einstein never accepted this view of quantum mechanics, saying, for example, that God doesn't play dice with the world. In the Copenhagen interpretation, not even God will know where we will find the electron when we look for it. So if you can, I would certainly encourage you to accept the Copenhagen interpretation. It will make learning quantum mechanics much simpler. But then you have to accept these mixed states which we really cannot visualize. And you have to accept that the actual act of measurement changes nature. We'll have more to say about this interpretation later on when we look at some experiments that have convinced most physicists that this is the most reasonable view of quantum mechanics. So let's take a look at the probabilistic interpretation, an interpretation which is completely consistent with the Copenhagen interpretation. If the electron is in the mixed state 0 plus pi, then there's a 50-50 chance of finding it in the left and the right hole respectively. So let's put the electron in an arbitrary state where phi 0 and phi pi are complex numbers. A second postulate of quantum mechanics is then the following. If we let P0 denote the probability that we'll find the electron in the right-hand hole, then P0 is equal to the formula for P pi, the probability that we will find it in the left hole, is similar, only replacing phi 0 with phi pi in the nominator. Remember from complex numbers that phi 0 square, phi 0 complex conjugate times phi 0. For example, let's say that the state of the system is given by I times 0 minus 2 times pi. In this case, the probability of finding the electron in the right-hand hole is I square divided by I square plus minus 2 square, which is equal to 1 over 5. And the probability of finding it in the left hole, P pi, is then 4 over 5.